US Physics Olympiad, year 2011, USAPHO, Semifinal exam. Problem B1. Solution for this problem you can find below this video in the description reference. An AC power line cable transmits electrical power using a sinusoidal waveform with the frequency 60 Hz. The load receives an RMS voltage of 500 kV and requires 1000 MW of average power. For this problem, consider only the cable carrying current in one of the two directions and ignore effects due to capacitance or inductance between the cable and with the ground. Question A. Suppose that the load on the power line cable is a residential area that behaves like a pure resistor. 1. What is the RMS current carrying in the cable? 2. The cable has a diameter 3 cm, is 500 km long, and is made of aluminum with a resistivity 2.8, 10 power negative 8 ohm by meter. How much power is lost in the wire? Solution. Because the load is resistive, we have power equal I RMS multiplied by V RMS. And from here we can find what is current RMS. That will be 2000 ampere. So that's the answer for first question. Second question. So first we need to count what is resistance for this power line, which is resistivity multiplied by length and divided by cross-sectional area, which is pi r square. And after putting numbers we will get 19.8 ohm. And to find what is power loss, we need to use this formula I RMS square multiplied by resistance R, which is 79.2 megawatt. So that's the answer for question 2 in part A. Part B. A local rancher thinks he might be able to extract electrical power from the cable using electromagnetic induction. The rancher constructs a rectangular loop of length A and width B less than A, consisting of n turns of wire. One edge of the loop is to be placed on the ground. The wire is straight and runs parallel to the ground at height h, much less than the length of the wire. Write the current in the wire as a function of omega and t in form of I0 sine omega t, and assume the return wire is far away. First, determine an expression for the magnitude of the magnetic field at a distance r from the power line cable in terms of I and r and the fundamental constants. 2. Where should the loop be placed and how should it be oriented to maximize the induced EMF in the loop? 3. Assuming the loop is placed in this way, determine an expression for the EMF induced in the loop as a function of time in terms of any of all these parameters and the fundamental constants. 4. Suppose that A equal 5 meters, B equal 2 meters and H equal 100 meters. How many turns of wire N does the rancher need to generate an RMS EMF of 120 volts? Solution. For the first question, result is pretty simple. Here we can use a regular Ampere law to find what is a magnetic field around the straight infinite wire. Due to radial symmetry, we have this integral equal to pi r b, and after that we can find the well-known expression for magnetic field around this wire. That will be this expression, which is a well-known result. That was the answer for question 1. Question 2. Where should the loop be placed and how should it be oriented to maximize the induced EMF in the loop? A solution for this second question is obvious, because we have this expression for magnetic field, so the total EMF will be larger when we put this loop directly below this wire, and the longest side of this loop must be oriented in the same direction as a wire. So that's the answer. The loop must be in the same plane as a wire, and we need to put it below the wire and as much closer to loop as possible. That's the solution. So first, using Faraday's law, we can find what is EMF in this loop. That will be number of turns multiplied by the change of magnetic flux per unit time. That's a dFB over dt. So we have to find what is magnetic flux for this loop. So magnetic flux will be this integral B by dA, where A is area for small parts of this loop, and due to some kind of symmetry we can represent it in this form. And now we can use this expression for magnetic field and put it in this integral. So result for magnetic flux is this one, but we need to find what is the change of magnetic flux with the time, and in this formula only current is a function of time, and the derivative from current by time equal I0 omega cosine omega t. And now we can put this expression in this formula and find what is EMF. So that will be full expression for EMF in terms of all these parameters in question 3. Question 4. To answer for question 4, we can use this result, but instead of I0 cosine omega t, we can put here I RMS, and instead of EMF RMS. So that will be this EMF RMS expression. Also, we need to convert omega to a regular frequency. So, using expression for regular frequency as omega over 2 pi, we have EMF for one turn loop, like this, and that's equal to 0.055 volts. And to get 120 volts, we need to use this number of turns, 7760. So that was the answer for question 4. Part C. The load at the end of the power cable changes to include a manufacturing plant with a large number of electric motors. While the average power consumed remains the same, it now behaves like a resistor in parallel with a 0.25 Hz inductor. First, Does the power lost in the power line cable increase, decrease, or stay the same? You need not calculate the new value explicitly, but you should show some work to define your answer. 2. The power company wishes to make the load behave as it originally did by installing a capacitor in a parallel with the load. What should be its capacitance? Answer. Solution. For the first question, if we put the inductor in parallel with a resistor, the total impedance will decrease as using Ohm law. Now we can use voltage, current, and impedance as complex numbers, and in this case we have Z. This expression. It means that now absolute value for Z is less than R. It means that Z decrease, I increase, current will increase. That's the answer for question 1. Question 2. The power company wishes to make the load behave as it originally did by installing a capacitor in parallel with the load. What should be its capacitance? Answer. To compensate the influence of this inductor, we need to put in parallel capacitors to cancel a complex part of this impedance. That will be this expression. From here we can find that capacitance must be equal to this expression, or in terms of numbers that will be 28.1 microfarad. So that's the final answer for problem B1.